Hello students, I am Sanjana Kavatagi, Assistant Professor, Department of Computer Science and Engineering, AITM, Belgavi. Let us continue with the video lectures on computer organization. In this video, I'll be starting with the module number 4, Arithmetic. So let us start with the module number 4, Arithmetic. So a basic operation in all the digital computers is nothing but addition or subtraction of two numbers. Okay, so arithmetic operations occur at the machine instruction level and they are implemented along with the basic logic functions such as AND, OR, NOT, exclusive OR, that is XOR, all these in the arithmetic and logic unit, that is ALU. Okay, which is nothing but the subsystem of the processor. Okay, so in this module we'll be presenting the logic circuits that are used to implement arithmetic operations. Okay, so the time needed to perform an addition operation that affects the processor's performance, and also we will be studying about multiply and divide operations which require more complex circuitry than either addition or subtraction operations. Also these will affect the performance. Okay, then we shall also see some of the techniques that are used in modern computers to perform arithmetic operations at high speed. Okay, so compared with the arithmetic operation, logic operations are also are simple to implement using the combinational circuitry. Therefore they require only independent boolean operations on the individual bit positions of the operands, whereas carry or borrow lateral signals are required in arithmetic operations. In logic operations these are not required, that is carry and borrow are not required in logic operations, so that is why they are little easier to implement. First we shall see addition and subtraction of signed numbers. This figure shows the logic truth table for sum and carry out functions for adding equally weighted bits xi and yi in two numbers x and y. Let us go through the table. For input 0 0, that is xi yi equal to 0 0, carry in for carry in ci will be 0, sum is also 0 and carry out is also 0. And for 0 0, carry in 1, then sum is 1, carry 0. Okay, so first we have x input, y input, and this is nothing but the carry input. When x and y is 0 and carry is also 0, sum will be 0 and carry out will be 0. When x and y 0 0, carry is 1, then sum is 1, there will be no carry. Okay, when x is 0, y is 1 and carry is 0, sum is 1, carry out will be 0. Okay, when x is 0, y is 1 and sum is also 1, so that time y is 1, carry in is 1, that time sum will be 0 and carry is 1. Okay, so when x is 1, y is 0 and carry in 0, sum is 1 and carry is 0. Okay, when x equal to 1, y is 0 and carry in is equal to 1, that time sum is 0 and carry out is 1. Okay, for x equal to 1, y equal to 1 and carry in is 0, sum is 0, carry out is 1. X equal to 1, y equal to 1 and carry in equal to 1, that time sum is 1 and carry is 1. Okay, for this the equation can be written as xi bar yi bar ci plus xi bar yi ci bar plus xi yi bar ci bar plus xi yi ci, which is nothing but the XOR of xi yi and ci. Okay, this is the equation for sum. Then the equation for carry out will be, that is ci plus 1 is yi ci plus xi ci plus xi yi. So these are nothing but the expressions for the functions sum and carry out. Okay, now we shall see one example for 4-bit unsigned numbers, that is addition of two unsigned numbers. The value of xi yi is 7 and 6, both are unsigned, which means they are positive numbers. So writing 7 in binary will be 0 1 1 1, that is 0 triple 1, and 6 will be 0 1 1 0. Okay, when we add these two, you can see first is xi yi 1 0, sum will be 1. Next for 1 1, sum is 0, with reference to this table, you can write sum is 0 and carry is 1. Okay, when xi is 1, yi is 1 and carry in is also 1, that time sum is also 1 and carry is also 1. Next is 0 0 1. 0 0 is xi y, 1 is carry in, but that time sum is 1 and carry will be 0. This is how simple addition will be done. Okay, here we should note that each stage of addition process must accommodate a carry in bit. Okay, so we use ci to represent the carry in into the ith stage, which is same as the carry out from I minus 1, that is I minus 1st stage. Okay, the logic expression that is written for si, that is sum, can be implemented with a 3 input XOR gate that is represented in the next part of this presentation, that is 6.2a from textbook. Okay, which is represented as a part of the logic required for single stage binary addition. Okay, so then for carry out function ci plus 1, this will be implemented with a 2-level and or logic circuit, which is convenient, which is a convenient symbol for the complete circuit for a single stage addition, that is called as a full adder, fa. Okay, so this is also shown in the figure, that is 6.2a from the textbook. Then a cascaded connection of n full adder blocks is shown in the figure B, that is 6.2b, and it can be used to add two n-bit numbers. Okay, since the carries must propagate or ripple through this cascade, the configuration is called as an n-bit ripple carry adder. It is called because the carries must propagate or ripple, both have the same meaning, through these cascades. So the configuration is called as n-bit ripple carry adder. Then the carry in C0 into the least significant bit LSB position, it provides a convenient meaning of adding 1 to a number. Okay, for example, forming the 2's complement of a number involves adding 1 to the 1's complement of the number. That is how you get the 2's complement of any binary number. Then the carry signals are also useful for interconnecting k adders to form an adder capable of handling input numbers that are kn bits long, which is shown in the figure C. Okay, that is cascade of k n bit adders. That is the logic for addition of binary vectors. All these diagrams represent the logic for addition of binary vectors. Now we shall see addition or subtraction logic unit. Okay, the n bit adder that is shown in the figure 6.2b, that can be used to add 2's complement numbers x and y, where the xn minus 1 and yn minus 1 bits are the sign bits. So in this case, the carry out bit cn is not part of the answer. Okay, so carry in bit is not considered as the part of the answer. Okay, we'll be discussing a concept called as arithmetic overflow in the next video. So this overflow can occur when the signs of two operands are the same. Okay, so there is a term called as arithmetic overflow. It can occur when the sign of the two operands are same. Okay, so in that case, overflow will be obviously occurs if the sign of the result is different. If the sign of the operands is same and the sign of the result is different, that time the overflow can occur. Therefore, there has to be a circuit to detect a overflow that can be added to the n bit adder by implementing the logic expression. So the logic expression for overflow can be written as xn minus 1, yn minus 1, s bar n minus 1 plus x bar n minus 1, y bar n minus 1 and sn minus 1. Okay, so it can be shown that overflow occurs when the carry bits cn and cn minus 1 are different. Therefore, a simpler alternative circuit for detecting overflow can be obtained by implementing the expression cn XOR cn minus 1 with an XOR gate. Okay, so in order to perform the subtraction operation, x minus y on 2's complement numbers, x and y, we perform 2's complement of y and then add to x. So this is how subtraction of two numbers is done. X minus y is done by finding the 2's complement. uh, this will be usually done on the 2's complement numbers x and y. So first we need to find the 2's complement of y and then add it to the value of x. Okay, then the logic circuit network that is shown in the figure 6.3 can be used to perform either addition or subtraction based on the value that is applied to the add or subtract input control line. Okay, so first this line will be set to 0 for addition by applying the y vector unchanged to one of the adder inputs along with a carrying signal C0. Okay, C0 of 0. So when add or subtract control line is set to 1, the y vectors is once complemented, that is each bit of this value will be complemented by the XOR gates, and C0 will be set to 1 to complete the 2's complementation of y. Okay, so also you should remember that 2's complementing a negative number is done exactly the same manner as it is done for a positive number. Okay, and then an XOR gate can be added to this figure to detect the overflow condition, that is Cn XOR Cn minus 1. Thank you for watching.